Hello, ladies and gentlemen. Today we're going to be talking about rational exponents and radicals, and we're going to see how they're related. So we're going to be converting between the two forms, and we're going to talk about what a rational exponent is. We should already be familiar with what radicals are because they're just the square root stuff, but we're going to be adding more of that kind of notation, ideas. We're going to be adding some new information to that stuff in regards to radicals, and what that new stuff is going to be called rational exponents. So what you're going to need today are your notes, pen or pencil, a calculator, all that fun stuff, and the foldable that goes along with this video. So in math, whenever we have something new, we always go over the vocabulary and then of course the new notation, because in math, we always have notation. That's why some people say math is a language or something that we have to interpret, because of the notational things that are different in mathematics compared to other classes. So this new vocabulary notation, we know that radical things have square roots or roots involved. Rational exponents, when we say rational, we mean like a fraction. So we're talking about radicals, and then rational exponents are fractional exponents. So on the left-hand side here, we have the x root of 12. So what do we mean when we say that? Well, the radical is the symbol itself. The number underneath, or the variable underneath, is called the radicand. And then the index is something that you maybe didn't even know existed, because we're so used to having the radical alone. So if we just had like the square root of 9, when we say the square root, our index is actually a 2, because that's what we mean when we say square. So the radical or the root is just the actual bar with the little tail on it, like a division bar, and the index is telling me what root I'm taking, whether it's a square root, a cubed root, and we're going to talk about that later in the video. So fractional exponents then are saying like 9 to the 1/2. So here, if I write the square root of 9, how that relates to the rational exponents is 9 to the 1/2. Every single radical can be written as a rational exponent. So if we have the second root of 9, it's the same thing, or it's equal to 9 to the 1/2. So when we convert between the two, when you convert, obviously it means equality. So whether you have 9 to the 1/2 or the square root of 9, it's the same thing. Okay, so that's what we're talking about today. So radical is just the symbol, the index is telling me what root I'm taking, and the radicand is the thing underneath, or in the rational exponent form, it's the base to that fractional exponent. Let's get a little more practice. You don't have to write this down in your foldable, but we're going to talk about converting between the two. So the question is, how are roots related to rational powers? And we talked about it a little bit on this last slide. But 25 to the 1/2, just like we did 9, is the same thing as the square root of 25. So that denominator becomes the root that we're taking, or the radicals index that we're taking. So 25 to the 1/2 is the same thing as the square root of 25, and the square root of 25 we know is plus or minus 5. So then 36 to the 1/2 naturally would be the square root of 36, which is plus or minus 6. 49 to the 1/2 is the same thing as the square root of 49, and the square root of 49 is plus or minus 7. 64 to the 1/2 is the same thing as the square root of 64, and the square root of 64 is plus or minus 8. Remember, when we take square roots, we always have a plus or a minus, because negative 8 squared is 64 and positive 8 squared is 64. So when you take the square root, don't forget your plus or minus. What about if we didn't have a 1/2 power? What if we had a 1/3 power? So what's happening now is we have the cubed root of 8. Well, when we had the square root of something like 9, we knew that it was asking us what to a power of 2 gives us 9. and we know that 3 to the power of 2 gives us 9. So if we have the cubed root of 8, now we're asking what to the power of 3 gives me 8. So what number times itself 3 times gives me 8? And that would be 2. 2 times 2 times 2 is equal to 8, because 2 times 2 is 4 times another 2 is 8. So we've always talked about perfect squares. There's also things as perfect cubes, perfect um, fourths, perfect fifths. There's still all that stuff. So when we say that we have a power of 1/3, it's the same thing as the third root or the cubed root. So we're talking the cubed root of 64 for this guy. So we're asking ourselves, what number multiplied by itself 3 times gives me 64? Or what number to the third power gives me 64? And that number would be 4. 4 times 4 is 16 times another 4 is 64. So the cubed root of 8 would be 2, and the cubed root of 64 would be 4. So we don't have to write this down in our notes. I just wanted you to follow along so that you can see how rational exponents don't just work for 1/2. They can work for anything else, like even a third root or a fourth root or a fifth root. So that's just breaking this down and explaining this a little bit further. Okay, so back into our foldable now. Throughout in the entire video or the entire lesson today, we're asking ourselves the questions, how are these two things related? The rational exponents and the radicals. How are they related to each other? So we're going to go through this table to explain a little bit, even if you haven't understood it yet, how they're explicitly related. So if we have a rational exponent of x to the 1/2, and remember rational means a fraction. So if we have an exponent that's a fraction, in this example, it's 1/2, that means that it's the square root. And how we write that in radical form is simply the square root of x. We're used to that, okay? If we've been given a rational exponent of x to the 1/3, that means that it's taking the cube root, and how you write that in radical form would be the cubed root of x, or see how there's a little index on that guy right here. So when we say the cubed root or the square root or the fourth root or the fifth root or the 17th root, that is the index that we're talking about when we go to radical form. And then last but not least, if we have x to the 1/4, that means that it's the fourth root. And then how you would write that in radical form is the 4 being the index, and that would be the fourth root of x. So when you see these things, let's go through this last row. When I talk about rational exponents, this is the language that I use. X to the 1/4. When we talk about exponents, it's the base, which in this case is x, to the 1/4. And then when we go to radical form, how we say that language is the fourth root of x. Okay, so make sure you're not only understanding visually what's happening in the two notations, but how to change our language between these two forms. So when we talk in class, don't say x1/4, say x to the 1/4, or the fourth root of x. Don't go 4 divided by x, it's fourth root of x. So make sure you're understanding how to verbally talk about these things as well as understanding visually what's going on. So far, everything we've had in this example has been to a fractional power where the numerator is 1. So what if we had something like 8 to the power of 2/3? What do we do when that happens? Well, we know that this, from what we've known about the last couple of slides, this is going to change to the index. So I know that I have a radicand of 8 and that I have a cubed root going on. But what happened with the 2? Well, think about if we just had 8 squared. How would we write that? Exactly how you see it, 8 to the power of 2. So when you have 8 to the 2/3, 2 is still technically your power or exponent that 8 is getting raised to, or the numerator is. So it's the cubed root of 8 squared, Or you can also write it like this, the cubed root of 8 squared. But either way, what we need to know about, here I'll rewrite this, what we need to know about 8 to the 2/3 is that this 3 in the denominator, or the denominator, becomes the root, and the numerator stays as the power. So the numerator stays as the power, and the denominator becomes the root that's happening with that index, okay? You don't need to write this down unless you want to, but that's what we're talking about today, is not just any or not just 1 over something, but any fraction as an exponent. Okay, so let's put what we just talked about on the last slide into our notes. So changing between the two forms. Radical form naturally has a radical sign or a root involved, whereas rational exponent form has the exponent that's a fraction or can be written as a fraction. So when we talk about which form are we in, whether you have a root involved is radical form, or whether you have a fraction involved is rational exponent form. So rational exponent form would be this guy, rational form, and this one would be radical form. And just like the last example, or the last slide, I should say, that we listened to, when you have a to the m over n, you can rewrite that as a to the 1 over n, and then the a to the 1 over n changes to the nth root of a, all still getting raised to that power of m. So we go from a to m over n, or a to the m over n goes to a to the 1 over n, all to the power of m, and that's all equal to the nth root of a to the power of m. Okay, so that's how we're converting back and forth, and it also can go the other way. So it can go from radical form to rational exponent form. But I think that's written down for you. So make sure you get these definitions of the radical form and rational exponent form. All right, let's look at some examples. So our directions tell us to rewrite the expression using radical notation or radical form. So we need to change these all to have a radical or a root involved. So if we have 7 to the 1/2, that's the same thing as the square root of 7. Now if we have 4 to the 4/3, remember this denominator becomes the root. So it would be the third root of 4, all raised to the power of 4. Okay, now moving on to example number 3. If we have 2 to the 5/3, 3 is going to be our index, so it's going to be the cubed root of 2, and that's all still getting raised to the power of 5. So now moving down to number 4. If we have 7 to the 4/3, 7 is getting cubed rooted. So the cubed root of 7, all raised to that numerator, is still going to be our power. So all raised to the power of 4. So the denominator is going to be the index, and the numerator is the power. Okay. Number 5, 6 to the 3/2, that's going to be the square root of 6, all raised to the power of 3. And then if we have 2 to the 1/6, that's going to be the 6th root of 2 raised to the power of 1, but you really don't need to put it in parentheses raised to the power of 1, so we're just going to leave it as the 6th root of 2. So make sure you get these examples in your notes. Okay, so now we're going to work the other direction for these 6 problems. We're going to write the expression using rational exponent form. So we want to get rid of all those roots, and we just want exponents that are fractions. Okay, so if there is no index written, so like in number 1, we don't have a number here, we assume that it's a 2 for the square root. Okay, so we have the square root of 10 all raised to the 3rd. Well, remember, when we convert between the two, this power is the numerator, and this index is the denominator. Okay? So it's going to be 10 raised to a fraction, where 3 is the numerator and the denominator is 2. Okay, if there's no power, we assume that it's 1. So we have the 6th root of 2 raised to the power of 1. That changes into rational form as 2 to the 1/6. If we go to number 3, we have a base of 2. We're going to have a fraction as our exponent, and we're going to have 5 over 4, because that power is my numerator and the index is my denominator. Number 4 is going to be 2 to the 1/3, because remember there's no number for the power, so we assume it's 1. And same thing for number 5, there's no power, so we're assuming it's 1. So we have 10 to the 1/6. And last but not least, for number 6, we have 10 to the 7/3, or 7/3. So hopefully you guys are starting to get used to converting between the two and seeing how these two things are related with these 12 examples. And if you still don't get it, that's why we're going to work on it together in class when you come back after this video. But we're going to do a couple more problems. Some of you have probably been wondering along this video, well, we've been able to plug in exponents to our calculators before, so if I'm actually finding a value for this, how do I do it in my calculator? Well, if you have a calculator like this one, what you're going to do is what your screen will say. It won't say this. That was just a picture that calculator had online. But what you're going to type in up here is 256, and like we've learned before, you're going to use the caret button, which is this button right here. So you'd be punching 256 caret, and then you would need a set of parentheses for 1 divided by 4. So if you're trying to find what this actual value is, you'd be typing in your calculator 256 caret parentheses 1 divided by 4 end parentheses, where this is your caret button on these types of calculators, okay? And same goes for 32. It'd be 32 caret parentheses 1 divided by 5 for those actual values. So nothing, you don't have to write anything down for this slide. I'm just showing how you would actually find this value in a calculator, okay? How would we find the value of the calculator in a calculator if we weren't given in fractional form? So we know we could convert this to rational exponent form, but what if I just wanted to try to use the cubed or fourth root in a calculator like this? So what you're going to have to do is you're going to have to, on calculators like graphing calculators, if you click the math button, I'll write that, if you click the math button in your calculator, you're going to have the option where you can do the cubed root, or so you have the option, which is option number 4. You could have the cubed root, that's what it looks like. And then option number 5, if we want something larger than a cubed root, they have this little X and then the radical sign. This is the one that you would want for something larger than a cubed root. So if you click the math button, and then you see these options listed, once you select that or hit enter, you can, what will happen is they'll have a little dotted box like this on the screen. And so you can use your arrows to go up here and put in a 4, and then you can arrow back to punch in a 625. So that way you can figure out how to do the fourth root of something. So you can use your calculator both ways. You can find it by typing in like -8 to the power of 1 divided by 3, or if you have a graphing calculator, you can use the math button to actually use the radical form right away, and you don't have to do any converting. If you guys have any questions about either calculator and how to find these values, when we get to class, you can ask me so that we're all on the same page and we know exactly what we're doing. And always feel free to use the graphing calculators in our classroom so that you can get used to both forms if you really want to. But again, you don't have to write anything down for these two slides. I just wanted to show you how you can do that in your calculator. Okay, well, what about when people didn't have calculators before? Like, what did people do if they were having to evaluate these things without a calculator? Well, I gave you another little half sheet. That's the perfect roots table, and you're going to want to have this glued in your notebook to reference. And this is a table that explains that this is just the number, and then if you were to square it, this is the list of perfect squares. If you were to cube these numbers, then this would be the list of the perfect cubes. If you would want to raise all the numbers to a fourth power, this is the list of perfect fourths, perfect fifths, all that stuff. So this should be glued into your notebook, or if you didn't pick one up, you're definitely going to want one of these. Okay, so let's try a couple by evaluating without a calculator. Like if you didn't figure out how to use a calculator, you can also figure out how to do this without a calculator, okay? So in example 1, we have 25 to the 3 halves. And we can rewrite this as the square root of 25 to the third. Well, if we look in our perfect squares list, we know that the square root of 25 means that it's 5. So the square root of 25 is 5. So what we're saying now is that the square root of 25 is 5, and that's all getting raised to the third. So if we go 5 cubed, then we know our answer is going to be 125. Okay? And in example 2, now we have 125, and we have the cubed root of that, and we're raising all of that to the negative 2. So if we look in our perfect cubes list, we know that 125, the cubed root of 125 from the previous problem is 5. So this becomes 5 all raised to the negative 2. So that's how we used our perfect roots table. And now it's just remembering exponential rules. When we have a negative exponent, that means we have to move it across the fraction bar. So we're going to have to move 5 squared to the bottom half of the fraction bar. So it's going to be 1 over 5 squared. And we know that 5 squared is 1/25. So 25th to the negative 125 to the negative 2/3 is the same thing as 1 over 25. Okay, so that's how you use your perfect roots table for evaluating without a calculator. Okay, so for these last two problems, example 3 and example 4, I want you to try on your own. Okay, so we're going to check these when you get back to class and make sure that you did them correctly, but I want you to try some on your own, okay? So thank you all for taking such good notes. I hope this video wasn't too long, and I hope you're understanding how to operate with your calculator, how to convert between the two forms, and all that good stuff. So make sure you get these notes written in your foldable and you get these two examples done, and I shall see you soon.